screen and this part of the video, essentially you've learned how to create the geometry. It's a simple shell and tube, and you can extend this design to further create more complex geometries. For example, if you have a tube that has 2 passes in one shell or 4 passes in 2 shells, essentially you can extend this and use your creativity in SolidWorks to create that. Now we're going to do this flow simulation. Again, the concept is going to be the same between different geometries. It's just the matter of the volume of calculations happening and the level of creativity that you have. But don't forget, again, I told you before, but I'm just repeating, don't put anything and then expect good results. So you should be careful about your geometry. You should make sure that the geometry is well defined and well contained. Don't create a shell that has an opening somewhere and it's loose. It can happen very easily because the geometry is more than what you see usually is more complicated, and it can be problematic from time to time. Okay, again, we go to make sure we have the flow simulation active. Okay, now I have the flow simulation added here. So I go through the wizard. So I'm going to create a project with the name of shell and tube, tube study. And I'm going to make sure the system is SI, the base parameters are defined well. Move forward. Essentially, this is obvious that it's an internal flow simulation with heat exchange between fluids, and we have heat conduction, but it's not in solids only. So then we go add water to our working fluids. So we have water here, add, and also we need to add stainless steel. We leave this flow type as default. And then from the solids list, we should find stainless steel. So in the predefined list of alloys, so we have in the alloys, if we scroll down, we have 2 stainless steels. I mean, we have 4 steels, 2 of them are stainless steel. This is what you normally see for heat exchangers. We pick the 321 as a default solid and then move on. So the default outer wall thermal condition is going to be adiabatic, which is the normal assumption for heat exchangers. So we leave it as the default. Again, for initial conditions, we just leave it as default and we move forward. So because the system is not closed by us, we have caps, open ends for our tubes. It says it's not watertight, meaning that if I run the fluid in the systems, it's going to leak. Do you want to create lids? Say yes. And we go to the back view and we select this face here. And then this cycle continues. So essentially it's running the simulations that it had, the algorithms, and it checks different views and then says, I need to redo the mesh. It's not watertight. Again, we should select another face. So this time we go to the front face. Oh, just didn't go through the front. Yes. So we select this face. Say yes. Again, the geometry have been changed. Do you want to reset computational domain? Yes, please. But the computational domain needs to reset the mesh setting. Yes, do it. And then this is good now. Now still we can see it's not very well defined. We are not expected to have that. So we do another create leads section again. So still it's not perfect. So we can go to this menu here to create another lid. And then this time we go to the bottom view. Remember, we have two extensions here and here that they need to be capped. So we go to the bottom view. And we can zoom in here. Again, create the lid, select this ring here. Again, if you rotate it, you can see where it is. It's the end of the tube. Same story. Yes. Again, another lid needs to be created. This time we go to the top view. And we need to create another lid. This point here is not being selected. So create the lid. We select the top view. And we select that face. And then hit OK. Reset the computational domain. Reset yes for the mesh. And this should be good. Now we select the left view. And what we need to do is just rotate a little bit and zoom in. So now that we zoomed in, we have this input data folder, and we are going to put the boundary conditions and initial conditions here. So we're going to insert a boundary condition here. And then we right click on this tube and select other. So from this list, we can select different surfaces. So we go down and up and find out what is what. Essentially what we are going to select, select other. I wanted to have the inner ring of the inlet port. This. Okay. Now the inlet mass flow for this one is going to be 0.2 kilograms. 0.2 kilogram per second. We assume it's uniform, and temperature is going to be 343.2 Kelvin. And hit OK. Oh, so I should correct that then. So the definition. So this face is wrong. Delete, and I should correct this selection. Let's see if it works. Okay, that worked. So we selected this lid 1 area. Now we have this inlet mass flow. We just rename it a little bit so we have a better definition. I'm gonna just rename inlet mass flow for tube. Now we zoom out a little bit. We insert another inlet boundary condition for this entrance here. So I'm gonna select other here. It's not working, no. So it's select other. What is going on? Set boundary condition. Good, better. Okay. Select other. And I want to see this face. This inner face here. You can see it in light blue. So the flow rate for this one is 0.8 kilogram per second. And the temperature is 283.2. Okay, and again rename this one to for shell. So we save it just to make sure that the software is good with us. We zoom out and then pan to the other side. Now we want to have a pressure opening on these sides. Now again, insert boundary conditions. No. And this ring and this ring here. Okay. I want this lid to be a pressure opening. So it's going to be a pressure opening and to the environmental pressure. And then click OK. And now we have this environmental pressure. We rename this to tube. And then for this ring here, we insert another boundary condition. Okay. For this lid, again, pressure opening. For the shell, it's going to be to environmental, and just rename this now. We're done with the boundary conditions. We can insert goals, and we can insert global goals for the temperature. We just need to go through the list and find temperature here, min, max, average for the solid, not the fluid. Here at the end. And then that's it for global goals. We are ready to move forward. Save before running. We can just hit run at this point. And I'm using Citrix at Rowan University, so I'm using their resources. Mesh is already started before, so it's a new, and also it's a new calculation, so we can start the run. I'm gonna pause this here because it's gonna take some time to run, but you can see the progress of the goals here and also plot the goals.